So, good evening. My name is Professor Sunando Dasgupta, and I am teaching transport phenomena to all of you. And some of you may have some queries which you would like to clarify. There could be some questions from the assignment. So, I have with me one of the TAs of the course, Ganesh Subramanian. So, he will also assist us and to clarify any doubts that you may have. What I would like to stress at the beginning of this session itself is that I wanted to give you an unified treatment of heat, mass and momentum transfer. The aim of the course was to show you that all these seemingly different transport processes follow same set of rules. That is, just to give you an example, that any transport is going to be proportional to a cause, and the cause, let us say for heat transfer would be temperature gradient, for mass transfer it is going to be concentration gradient, and for velocity or momentum transfer it is going to be velocity gradient. So, starting with the similar nature of the defining equations of these transfer operations, I then went into the derivation of Navier-Stokes equation, which would give you a fundamental insight into the momentum transfer process, and I have introduced in the class itself how the momentum equation or the Navier-Stokes equation can be simplified in order to give you a governing equation which can be integrated with the help of boundary conditions, appropriate boundary conditions to arrive at the velocity expression, the distribution of velocity in a flowing fluid. And once I have the velocity distribution, then if it is a Newtonian fluid, then I can use Newton's law of viscosity in order to obtain what is going to be the shear stress. What is going to be the shear stress at the junction between the liquid and the solid, at the interface between the liquid and the solid, which would give us some idea of the drag force. So, this was the first part of the course in which we derived, discussed, and we went on to work with Navier-Stokes equation to derive the governing equation for any such process. Then we understood that same set of principles can also be applicable for the case of heat transfer, but heat transfer is slightly more complicated as we have a coupled situation where the heat transfer is going to depend on the velocity distribution. So, velocity or rather the momentum transfer and heat transfer are coupled. There is a one way coupling between fluid mechanics and heat transfer, and in a similar fashion the mass transfer equations can also be derived. So, for the case of heat transfer we have derived the energy equation, and again we start with the energy equation, the full form of the energy equation. We simplified by cancelling the terms which are not appropriate, which are not relevant for a given situation, and then we arrive at the governing equation, which when solved with the proper boundary conditions would give me the temperature distribution. And similar to shear stress, the defining the engineering parameter of interest is the heat transfer coefficient. So, how could we get an idea of the heat transfer coefficient? What are the parameters on which the heat transfer coefficient would depend on in a flow system? That was also discussed in the course. Then we went on to mass transfer and the species balance equation, that is what we have derived, and then we could see that the species of the concentration of a specific species can change as a result of convection, as a result of conduction, and also there could be some reaction which is taking place in the medium converting one species to another. So, that source or sink term should be included in the governing equation. So, we have got a species balance equation, and then again as before we cancel the terms which are not appropriate, and we obtain the governing equation, and with the help of boundary conditions we got the concentration distribution. So, these were the three major pillars on which the transport phenomena course stands, and we then went on to slightly more complicated phenomena. But before that I should once again talk about the relevant boundary conditions. When we talk about momentum transfer, the boundary conditions that we have used so far are the no slip condition. That means, when a liquid and a solid are in contact, then their relative velocity between the liquid layer and the solid layer would be 0. So, if a solid is at rest, then the liquid in contact will also be at rest at the vicinity of the interface between the liquid and the solid. But as we move away from the solid, there can be velocity in the liquid. So, no slip boundary condition is one of the most important boundary conditions in momentum transfer or in fluid mechanics. On the other hand, if it is a liquid vapor interface, liquid air interface, due to the drastically different viscosities of the liquid and the vapor, the shear stress at the interface would be 0. So, these two were the major boundary conditions which we have discussed in the course. Coming to heat transfer, the boundary conditions are continuity of temperature and continuity of heat flux. So, the temperature at a liquid solid interface on the liquid side and on the solid side would be identical. So, this is something similar to the no slip boundary condition which we have used in momentum transfer. So, there are other conditions like there could be a surface through which no heat can pass through, which is an adiabatic surface. So, the temperature gradient at that point will be 0, or in other words, dt dx at that location where the liquid is in contact with an adiabatic surface, a perfectly insulated surface, the gradient of the temperature would be 0. So, that is another condition which we have used. And I should mention that in a convective process, in a convection process, you cannot have convection without conduction. So, the liquid molecules which are in contact with the solid, they are static, and the principal mode by which heat can get transferred through this static molecules of liquid in contact with the solid is conduction. And once you cross that immobile layer of liquid molecules, you are going to have convection. So, conduction and convection both coexist in such a process. In the case of mass transfer, the relevant conditions are that you could know the concentration at a specific point. For example, if you have a lump of sugar in water, then the concentration of the sugar at the sugar water interface would be the solubility of the sugar in water. So, the solubility can define a concentration, a specific concentration at a given location. If you are far from the lump of sugar, then in that solvent there may not be any sugar present. So, at distance, as distance tends to infinity, your concentration over there could be 0. Now, let us say two molecules which are reacting, they are coming close to each other, and there is an instant reaction which is taking place. So, the concentration of this species which undergoes an instant reaction would be 0 at that location. So, that is another condition which we have used. So, I have shown you, I have solved a number of problems in class, and there were problems in the assignment as well. So, if you have any queries, we will try to answer them and clarify any doubts that you may have. We also spoke about the boundary layers, but that I will pick up in the second part of this interaction. So, if you have any queries on heat, mass and momentum transfer, their fundamental questions, the relevant boundary conditions, their applications and so on, then I will be happy to answer them. So, if there are any questions, please let us know, and we will see how they can be described, discussed and explained. And we will talk about boundary layers in the second part of this interaction. The boundary layers, the similarity between heat, mass and momentum transfer, the Reynolds analogy and so on. So, it appears that you have understood everything. You do not have any queries, which is good. Please feel free to post your questions, any doubts that you may have in the Navier-Stokes equation, in the energy equation, in the species balance equation, in how to get the velocity profile or the temperature profile and similar such situations. Any fundamental queries that you may have. So, this is a good opportunity provided by NPTEL to address the common problems in I and my TA would try to answer any questions that you may have. It could also be something that we have asked you at the during this assignments. If there are any mistakes that we have made, or if you think a problem can be done in a different way, a different approach, or you are not sure about the approach that we have taken, you would be happy to clarify them. So, before I get into the second part of the course, I just wanted to make sure that there are no unresolved issues in this part of the course. The velocity distribution, the temperature distribution and the concentration distribution. In typical situations that arise in industrial applications of these three transport processes. Is there any way to find out if anyone is there online?
There is 5% there, but it may reduce. Now 3 are watching.
Okay. So, a question is always welcome. It clarifies your doubts and it would also point to me about how should I teach from this point onwards. I mean, you probably remember one of the problems which I undertook towards the beginning. It's about flow along an inclined plate, and flow along an inclined plate, we have assumed that it's a steady state. We have assumed that it's an incompressible flow such that the density remains constant, and the flow is one dimensional. The flow is taking place because of gravity and there was no applied pressure gradient. So, we started with the component of the Navier-Stokes equation which is in the direction of the motion. So, if along the plate we indicate that it is the x direction where we have the flow. So, we need to choose the x component of the Navier-Stokes equation that I have shared with you during the class. So, the x component of Navier-Stokes equation when you apply for at the steady state, then the first term on the left hand side of Navier-Stokes equation, which is del V x del t, that would be 0. We also would understand that Vx, the velocity along the plate, is not a function of x, it is not a function of z, that is the plane perpendicular to the paper. However, it is going to be a function of y, which is the thickness of the film that is falling along the plate. So, due to no slip condition, the velocity at the liquid solid interface, that means at y equals 0 would be 0, whereas at y equals delta, where delta represents the thickness of the film, y equals delta denotes the liquid vapor interface. At that point, the stress would be 0, and the stress being 0 simply means dvx dy at y equals delta to be equal to 0. So, these two were the boundary conditions which are relevant here, and we know that there are no Vy component, no Vz component, and Vx does not vary with y. So, the entire left hand side of the Navier-Stokes equation would be equal to 0. And if you are looking at Navier-Stokes equation or looking at the class notes, you can see that there is a dpdx term on the right hand side. This dpdx denotes the imposed pressure gradient, and there is no imposed pressure gradient from outside by an external agency. So, that dpdx term would also be 0. And we also have the viscous terms. The viscous terms are simply mu, the viscosity, times d 2 Vx by dx square, which is 0 because Vx is not a function of x, d 2 Vx by dy square, which is non-zero, and d 2 Vx by dz square, which is again 0. And then I have the body force term, which is rho g x. So, the entire governing equation becomes 0 on the left hand side to be equal to mu times d 2 Vx by dy square plus rho g x, where g x is the component of the body force, the gravity in this case, in the x direction. So, it is a simple ODE which can be integrated twice and use the two boundary conditions, and you get a compact expression for velocity into the liquid film at any given point. And you can clearly see that the velocity distribution is going to be half parabola, with the minimum being on the plate and the maximum being at the liquid air interface. So, it is a half parabola. So, this velocity expression can then be also differentiated to obtain what is the shear stress exerted by the liquid on the plate. So, that shear stress multiplied by the area of the plate would give you what is the drag force being felt by the plate due to the motion of the liquid. In other words, you can find out what force needs to be applied on the solid plate in order to keep it stationary when it is in contact with a solid plate. So, when it is in contact with a moving fluid. So, this has implications in the designing of marine vessels, the design of aeroplanes and so on, where drag force plays an important role. So, this is the first problem which we have done for the case of momentum transfer. Again, any question on this? Okay. Then if you do not have any queries, then I would briefly tell you about the second part of the course and wait for any responses from your side. The second part of the course deals with the concept of boundary layer, because most of the phenomena that we encounter in any chemical industry happen at the interface. So, if it is momentum transfer, if it is heat transfer, or if it is mass transfer, the phenomena take place only at the close to the boundary. So, you have a situation in which the velocity gradient exists at a point very close to the surface, the temperature gradient exists at a point very close to this. Okay, we have our first question, in which what I can see is there is a solid vertical plate, and we have two fluids which are apparently flowing down, fluid A and fluid B, and the films are of equal thickness. They could also very well be of different thicknesses as well. So, in this case, if the governing equation would simply be there is no pressure force. So, the governing equation would simply be the mu times d2 v y dx square, because you have v y which is the non-zero component, there is no v x, it is a laminar flow, and there is no v z. So, v y is the non-zero component, and v y changes with x, it does not change with y, it does not change with z. So, the governing equation for both the fluids would be mu corresponding to fluid A, let us call it as mu A. So, mu A times d2 v y dx square plus rho g, since your y is in the downward direction. So, g would be positive. So, your governing equation would be mu A d2 v y by dx square plus rho g would be equal to 0, and the same would be the governing equation for fluid B, only difference being the viscosity would be replaced by mu B. So, two equations would be identical except mu A for fluid A and mu B for fluid B. Now, we have to write what are the boundary conditions. If I think about fluid A, it is in contact with the solid. So, V y for fluid A would be 0 at x equals 0. That is the no slip condition, which is the first condition. Similarly, if I think about fluid B, on the rightmost side, the fluid B is in contact with air. I suppose the right hand side is air. So, the velocity of fluid B v y b at y equals to at x equals to delta, that means at the liquid air interface would be maximum. So, dvy by dx at x equals to delta would be 0. So, that is your second boundary condition, but you need two more boundary conditions to solve the velocity profile for these two cases. Now, as I said, there would be velocity continuity at the interface. So, whatever be the velocity of the fluid A at the interface between A and B must be equal to the velocity of the fluid B at the interface. So, V A at x equals delta must be equal to V B at y equals delta. So, I can if I could point out over here, I do not know how to point out. Okay. So, over here at this point, that means at x equals 0, at this point at x equals 0, you have the velocity to be equal to 0. At x equals 2 delta, the shear stress is going to be 0. So, that means the velocity gradient for fluid B would be 0, but at x equals delta, the velocity of A and the velocity of B would be equal. So, these are the boundary conditions which you would use in order to obtain what would be the condition for this. Okay. I think I am clear, but if you have any more queries, I would be happy to answer. And as I mentioned, the main point one has to make is the velocity continuous at the interface between two liquids. That is the condition which is to be used. Are you satisfied with the answer or you want more clarifications? So, 4 conditions: no slip, no shear, continuity of velocity. The velocity profiles would look different in the two fluids, but the velocity at the interface must be equal to each other, and velocity on the solid plate would be 0. Velocity gradient at the air fluid B interface would also be 0. So, in one case velocity is 0, the other case the velocity gradient is 0. So, if there is any more question or a continuation of this question, I would be happy to answer that. Please feel free to post your questions. So, I believe that you do not have too many queries, and you are with me during the teaching of this course, and at any point of time, if you have additional questions or you want a topic to be discussed in more detail, or you want a specific problem in the assignment sheet or elsewhere you want more clarity on it, please let us know, and the TAs and myself would try to resolve it. So, I hope that you will continue to feel attracted towards this unique course of transport phenomena, which bridges the seemingly different processes together and tries to give you a unified view of the processes. So, best of luck with your studies, and I hope to interact with you soon and see if you have any more questions. Thank you so much.